Hello and welcome to Mr. Linford's math course. In today's presentation, we're going to be continuing an exploration into the applications of single variable linear equations. This time we're going to focus on what are called distance, rate, and time problems, or more commonly, uniform motion problems. We're going to go over some terms to know about in this video for these types of problems. Then we're going to actually practice these applications in a couple different senses, and then what we're going to try to do is define a general form to the way in which these problems are solved. Now, before we begin, when working with a distance, rate, time problem, you need to know of the three different quantities that are interacting with each other. You're talking about distance, such as distance traveled, rate of speed, that is how fast an object or objects were traveling at, and then of course time being the time interval of travel. So those three components all work together to set up the various equations we're going to work with. They're in fact related in a very specific way. The main sense that you can think of the relationship between distance, rate, and time is that distance, and we'll abbreviate that with a D, is equal to the rate of speed, we'll call that R, times the time interval T. And this should make sense. This general setup it's pretty standard for us. I always say to students, well, think of the example. You travel 200 miles per hour for, let's say, I'm sorry, I wrote 2. You traveled 200 miles per hour for 4 hours. How far did you go? And let's just say distance. Oh, great, my stylus is already dying on me, and I just started the video. All right, distance we're not sure about, okay? But you know you went 200 miles per hour for 4 hours. Here's the rate. Here's the time. How do you figure out how far you went? Well, most people would just say take 200 miles per hour and multiply that by 4 hours, and you will end up with 800 miles. So you have the rate, the time, and the distance. Now, some people will refer to this relationship in different formats. So this is what I think is the easiest format to remember because you can come up with a quick example to prove it to yourself. But sometimes people will have it where they've divided the time over and they'll have distance divided by time equals the rate of speed. And that's fair too. All that you did was you just divided both sides by time. So these two equations are in fact equivalent. Let's see some other equivalent equations we might have. Time is equal to distance divided by rate. This is where all we did was divide R on both sides, and you would end up to this equation. So these relationships, they're all equivalent to each other. They're all pretty much the same thing. You just have to decide which you prefer to work with. For our examples, I am going to be working with this setup. Distance is equal to rate times time, because generally speaking, this is the standard approach you'll see in most textbooks. So let's get into the first application problem. We're going to take a look here and try to see if we can identify, one, the relationship between the distance, the rate, and the time in this example, and then to try to find which of those is missing. So, in this problem, Mr. Rosewig can hike 1 mile per hour faster downhill to Moose Lake than he can hike uphill to the campsite. If it takes him 3 hours to hike to the lake and 4.5 hours to hike back, what is his speed hiking back to the campsite? Okay, we read through the problem. What are we trying to find in this problem? Well, hopefully you're saying that we are trying to find his speed, and more specifically, we are trying to find Mr. Rosewig's speed hiking back to the campsite. So speed to the campsite is what we're trying to find. What key information do we have here? Well, he can go 1 mile per hour faster downhill than he can uphill, and that should make sense. Can't you go faster downhill than uphill when you're fighting gravity? Also, we know that it takes 3 hours to hike to the lake and 4.5 hours to hike back. So 3 hours downhill, 4.5 uphill. There's a lot of information here, so what I like to do is draw a little diagram. So, oops, let me switch pens here. So let's draw a little diagram. I'm going to pretend like we have our little hill here. And let's say this is the lake over here. Here's Moose Lake, whatever. And we're going to say that this is the campsite right at the top of the hill. I know, great drawing. So let's say we're going to the lake. So Mr. Rosewig is hiking downhill. So he's going down to the lake. Then what happens? Well, Mr. Rosewig hikes back uphill. So here we have our hill again. Here's the lake. And here at the top of the hill is the campsite. This time Mr. Rosewig is hiking uphill. So to campsite. All right. Let's try to put this information in and assign it to each situation. So let's assign it to going down to the lake or up to the campsite. Now, we know that it takes him 3 hours to hike to the lake. So time here is 3 hours, while it takes 4.5 hours to hike back up to the campsite. So time equals 4.5 hours. Did I say that right? We want to hike 3 hours down to the lake, 4.5 up to the campsite. Now, we also know that there's this kind of relationship here between how fast Mr. Rosewig walks. Do we know how fast he walks? Were we told that information? Well, no, but you're given some relationship. You're told that he walks 1 mile per hour faster downhill to the lake than uphill. So the rate of speed, well, I don't know what it is going uphill, but I know that it's 1 more going downhill. And keep in mind, what is the speed hiking back to the campsite? This is what we're trying to find here. So I'm going to say the rate of speed to the campsite is x, and the rate of speed downhill to the lake is x plus 1. Okay? We don't know the exact number for the rate of speed, but we have a way of representing it. Okay? So we've let the variable represent what we're trying to find, and then we have this relationship set up here. So we have time and we have the rate of speed. Distance. Is there anything in this problem that tells us the distance of how far Mr. Rosewig traveled? Well, no. We have no indication of how far it is up and down this hill. So we can't work with the variable d, or the quantity d. Instead, let's try to use some symbols to represent what's going on here. Because basically, this is all the information we have. We have the 2 times, and we have ways of representing their rates. So what I'm going to do is I'm going to set up 2 equations. I'm going to say distance L, dl here, that's distance to lake. So the distance to the lake is equal to the rate of speed times the time it took. So how long he was traveling at that speed for. So in this problem, the time is 3 hours and the rate of speed is x plus 1. Let's also come up with an equation for the distance to the campsite. I'll call that d and c. So distance to the campsite here, dc, is equal to the rate of speed to the campsite times how long he was traveling at that speed for. So that distance, this distance right here, is equal to 4.5 hours times x miles per hour. So here are the 2 equations. We have the rate and time going up to the campsite and the rate and time going down to the lake. So you might be saying to yourselves, oh gosh, we're in trouble here. Because here's the problem. Yeah, we have the variable x, but we also have this unknown, distance to the campsite, and this unknown, distance to the lake. These are three unknown, these are basically three variables. We don't know how to solve with three variables. What are we going to do here? What I want you to do, and it's a very clever way of solving this problem, I want you to pause the video, take a minute to see if you can try to be a bit clever in your work here. We have this equation and this equation. From the given information, we're able to set these equations up. What can you say about these two equations so we don't really have to work with these unknown quantities, and instead we can just solve for x? What can you say about these two equations? Pause the video, take a minute, see if you can come up with an idea of how to get around this. All right, well, hopefully you were able to come up with the rather clever solution, but the idea here is really relying on how you're thinking about the problem. Remember, this equation deals with the distance to the lake. This equation deals with the distance to the campsite. Mr. Rosewig went down the hill, then he went back up the hill. Down the hill, up the hill, down the hill, up the hill. What do you notice about that? Well, hopefully you're saying to yourself, wait a minute. That's the same amount of distance, isn't it? If he goes from his campsite down to the lake, and he walks back the same way from the lake to the campsite, Mr. Rosewig has walked the same distance both times. So we can say that the distance to the lake is the same thing as the distance to the campsite. So, if the distance to the lake is 3 times x plus 1, and the distance to the campsite is 4.5 times x, set them equal to each other. This is one of the main setups to a distance rate time problem. This is where you completed the same trip twice. Rosewig went down the hill, and then he went back up the hill. Therefore, these which give us the distance must be the same thing. So that's why we're able to set them equal to each other. Then it becomes a very simple problem to solve. Make sure you distribute the 3 through. We're going to isolate the variable x. I'm subtracting the 3x from both sides, and I get 1.5x. And if we divide that on both sides, 3 divided by 1.5 is, I'll write it over here, 2. So Mr. Rosewig walked 2 miles per hour up to the campsite. Okay, that's what we were trying to find here. Remember, because this is something people tend to forget. When they start working with a lot of quantities and different variables and they're getting deep into a problem, they forget, what did the variable represent from the get-go? X was how fast Mr. Rosewig could walk uphill. So that was 2 miles per hour. How fast could he walk downhill? That would be 3 miles per hour. So for this problem, the big idea here was that distance to the lake equaled distance to the campsite. It was the same distance both times. That was the big idea for how we set these two equations equal to each other. Let's take a look at another problem, and let's see if we can figure out ways in which of representing these equations. So in this problem, we have 2 cars being 190 miles apart, and they are traveling towards each other along the same road. They meet in 2 hours. One car travels 4 miles per hour faster than the other car. What is the average speed of each car? I love these types of problems because they're very... anytime you watch a show about students in high school or preparing for the SAT or something, they're always asked this type of problem. And I don't know why, I just find them very entertaining. So in this situation, what do we have going on? Well, we basically have 2 cars racing towards each other. So let's have car 1 and I'll do green. Let's do car 2. I know, very amazing drawing on my part. So we have these 2 cars and they're racing towards each other. And they start 190 miles apart. So how far are they? So let's say they start and they're 190 miles apart. So that's one bit of information. And they are traveling towards each other. Okay? So They're racing towards each other. And they're going to meet in 2 hours. So the cars will meet. Now, keep in mind, one car is 4 miles per hour faster than the other. So in this problem, let's see. Well, I'll make car 2 faster than the other one. So this car is the faster car. And this car will be the slower car. So we have the faster car and the slower car, and they're going to meet in 2 hours. So would it be fair to have this drawing right here? No, because that's about halfway. Really, the faster car would have covered more distance. They both traveled for 2 hours, so maybe this would be a more accurate drawing, right? This would be the distance of car 2. And maybe I should write that in green, actually. Let's see here. Distance of car 2. And then I'll write distance of car 1 in blue. And it should make sense that car 1 is not going to cover as much distance as car 2 because it's going slower. And we know that the travel time, t, is equal to 2 hours. So they were traveling for 2 hours. One went farther than the other, but they meet eventually after 2 hours. Now, we have the time for both cars. It was 2 hours of travel for both cars. We have the total distance, actually, is 190. What about rate of speed? Actually, that's what we're trying to find, the speed of each car. So I need a way of representing the rate, and let me change colors here. Let's do that. Let's get the rate of car 2, which is the faster car, and the rate of car 1, which is the slower car. Well, I don't know what that is, and that's in fact what I have to find, so we should let them be variables. We could do x and y, but keep in mind we don't want to do 2 variables yet. We're not sure how to work with 2 variable systems, so instead let's work with 1 variable. You have this relationship here that one of the cars is 4 miles per hour faster than the other. This car is 4 miles per hour faster than car 1. So if car 1 was x miles per hour, car 2 would be 4 more than that, x plus 4. All we're doing here is I'm setting up the relationship. I'm letting one of these unknowns be the variable, and I'm letting the other one be the relationship, how it's built off of the unknown. If this is x, this is 4 miles per hour faster than that, okay? A big idea with algebra here is representing things that represent the relationship between what's going on. Okay, I have a way of representing the rates. I have the time each car traveled because both only traveled for 2 hours. So we should be good to set this up. Let's set up 2 equations here. I'm going to start with the slower car. Distance of car 1 is equal to the rate times the time. Well, in this case, the time is 2 hours and the rate is x. So 2x. The faster car traveled some distance. We call it d2. Distance of the second car, and that rate of time and rate of speed and the time traveled. Well, the time was 2 hours and the rate of speed is x plus 4. So you could say that it's 2x plus 8 represents the distance that car 2 traveled. Okay? What I need you to understand here is that this 2x plus 8 is equal to the distance, okay? I need you to understand that. I also need you to understand that the 2x here is equal to the distance that car 1 traveled. That's the thing about rate and time. When you multiply them, it gives you the distance. The number you produce is the distance that that object traveled for. In this case, the cars. When you multiply 2 and whatever x is together, you know how far car 1 traveled. Okay? So these boxed equations here don't represent rate and time anymore. We've multiplied them. They now represent the distance of each car. Because when you figure out what x is and you plug that number in, it's going to spit out the distance each car traveled, okay? That's what this represents. Why is that important? Well, again, like the previous problem, we need a way of connecting these two equations together. The trouble is we have the variable x here. We also have d1 and d2, how far each car traveled. That's three unknowns. We don't know the rate of speed x, and we don't know how far each car traveled. So what we need to do is find a way of combining these equations into one large equation. But how do we do that? In the previous problem, we said that the one distance and the other distance were in fact equal to each other. Remember, Mr. Rosewig went down from the campsite to the lake, and then he went back up the same way from the lake to the campsite. Is that true in this problem? Are these distances equal to each other? Well, hopefully you're saying right away no, because take a look at our drawing here, and we said that a couple minutes ago. We said they shouldn't be the same because one car went faster than the other. They traveled for the same amount of time, and one car was going faster than the other. Obviously, this car is going to cover more speed. So they're not equal to each other. In fact, D2 is probably greater than D1. The distance was much farther, probably. So, how else can we relate these? Because these two distances are not equal to each other. So we can't do what we did before. What I want you to do is pause the video, and this is where you really got to put your algebra hats on and think, how are these two quantities related? Because that's the thing I need to link together, these two distances. How is distance 1 and distance 2 related to each other? How are they related? What are they related to? How can we write one equation for both of these quantities? That's the task. So pause the video, see what you come up with. All right, hopefully this drawing was actually helpful to you when thinking about how the two distances are related to each other. So obviously they're not equal to each other. We know that right away. They can't be equal to each other. We can reason that out pretty easily. Instead, think about this drawing as a whole. Distance 1 and distance 2, how far car 1 went and how far car 2 went. We don't know, but we know all together they've covered 190 miles. Keep in mind, the cars started 190 miles apart. When they drove and they met, they've covered 190 miles altogether. Between the two of them, car 1 went some miles, car 2 went the rest of the miles, but altogether, they've covered 190. So this is the setup that we want here. Here is how distance 1 and distance 2 are related. They're not equal to each other like before, but this time they add together to make the total distance. Let's go ahead and let's sub in what we have here. Distance 1 is really 2x. And distance 2, we said to represent that by 2x plus 8. So we're going to set these, we're going to actually add these together, not set them equal. We're going to add them together and solve for x. So 2x plus 2x is 4x. We have an 8 here, and that's equal to 190. If I subtract 8 from both sides, I am going to get 4x is equal to 182. So then, to get x by itself, if I took 182 and I divided that by 4, we should get x is equal to 45.5 miles per hour. Here we found how fast car 1 is traveling. Car 1 is traveling 45.5 miles per hour. That's what x was. Remember, car 2 is however fast car 1 was going, but 4 miles per hour faster than that. So car 2 is 49.5 miles per hour. This is the main idea of this different type of distance rate time problem, where the distances aren't the same thing. They're in fact different from each other. And that's fine. We still have a way of representing how they're related. Okay? That's the big idea here. What I need you to do, anytime you do a distance rate time problem, try to draw a picture of what's going on and label the information. You'll see here I labeled the times that went with each car, the speeds that went with each car, I labeled the distances, etc. So make sure you're doing that just so you know which quantity is working with what. Let's try a similar problem. This time we're saying that vehicles are driving away from each other. So, 2 truck drivers leave a cafe. Here is the cafe. And they leave at the same time, traveling in opposite directions. One truck is 7 miles per hour faster than the other. After 4 hours of driving, they are 404 miles apart. So keep that in mind. Both trucks have driven for 4 hours. And one's going faster than the other. So one will have gone some distance. One will have probably gone a little further. So let me exaggerate this a bit. There. One went shorter distance, one went farther. So here is truck 1. That is a terrible truck. Don't judge me. Here is truck 2. Oh boy, whatever. So they've driven for 4 hours. This is obviously the faster truck, and this is the slower truck, okay? So this truck, we don't know its rate of speed. And in fact, that's what we're trying to find. So we're going to let it be x. The faster truck's rate of speed, we're going to let be x plus 7, because it's 7 miles per hour faster. So we have the setup. One went a little further than the other. We know a way of representing their rates. We know how far they we know how long they traveled for, and we know how far they traveled in total. They end up being 404 miles apart after this 4-hour time period. What I want you to do is first come up with an equation for the distance of the fast truck. We'll call this here df. And then this right here is ds, the distance of the slow truck. What I want you to do is come up with 2 equations, one for each, the distance of each truck. Then we're going to come back and see how we did. All right, well, hopefully this problem wasn't too bad for you. You'd recognize that in each problem, the time is 4 hours. We know how fast or how long each truck was traveling for. Now, the rates were different. We didn't know the rates, but we had a way of representing them. The slow truck was going x miles per hour, and we said the fast truck was going x plus 7 miles per hour. And if you simplify this by distributing, you could say 4x, oops, let me rewrite that here. You could say 4x plus 28 is the distance of the fast truck, while the distance of the slow truck is 4x. You have both of these equations here. What I want you to do now is write one equation that deals with the variable x, and that is the only unknown quantity in the equation. Okay? See what you can come up with, and then we'll check our work. So we need to first ask ourselves, how are the 2 distances related? The distance of the fast truck and the distance of the slower truck. Are they equal to each other? Well, no, obviously not. One car or one truck is going to go much farther than the other truck because it's going faster. It's traveling at a faster rate of speed. So they're not equal to each other. Instead, we have this information that altogether, the distance of each truck combined is 404 miles. So how far each truck traveled, both of those together makes 404 miles. So this is the setup we have, and it's pretty much the exact same. I was going to say it's similar. It's pretty much the exact same as the previous problem, except instead of driving towards each other, the vehicles are driving away from each other. We still have their distances adding up to a total distance. So we can go ahead and substitute in what each of these represents. The distance of the fast truck is represented by 4x plus 28, and the slow truck is represented by just 4x. We can add the like terms together to make 8x plus 28 is equal to 404. Now, to get x by itself, we first have to move over the 28. So let's take 404, and we're going to subtract 28 from it. That means 8x is equal to 376, and we'll divide that by 8 to get x is equal to 47 miles per hour. That's how fast the slow truck was going. 47 miles per hour. So how fast was the fast truck going? Well, if it was 7 miles per hour faster, that means it was going 54 miles per hour. So we now know how fast each truck was going. We could even figure out how far they traveled, because we know their exact rates and how long they traveled for. Again, the big takeaway here is knowing this setup, understanding this relationship between the distances. That is key to solving these types of problems. All right, let's now take a look at a fun Batman problem. In this situation, we're going to take a look at some hypothetical situations and try to compare these situations for an ideal setting. In this case, Batman is using his Batplane to fly 7,000 miles from Gotham City to the country of Bhutan to fight the League of Assassins. Now, Bhutan is a country in Asia. In Gotham City, we can assume it's kind of like a New York. So you can imagine that distance. And we're going to say it's 7,000 miles that he needs to fly. And it takes Batman 1.8 hours to travel to this country, Bhutan, at max speed. So let's draw a little picture of what's going on here. I'm going to put a point down and say that this is Gotham City. And I'll put a point here and say this is, oops, let me try to spell it properly, Bhutan. And let's say Batman goes from Gotham City to Bhutan. And we know that it takes him 1.8 hours to get here. And the rate of speed, well, all we know is that he traveled at max speed for the Batplane. Don't really know what that is, so, well, we're going to have to leave it as a blank for right now. So then, let's keep reading and see what happens here. After fighting the League of Shadows, Batman gets a distress call from Gotham and must return immediately. Okay, so now he's got to go back from Bhutan to Gotham City. Okay, so he goes from Bhutan to Gotham City, and as he's traveling, the wind has picked up. What's happening is the wind is slowing down the Batplane. It's pushing against it, making the Batplane travel 207.6 miles per hour, less than what it went when it went to Bhutan. 207.6 miles per hour, less than max speed. So Batman needs to figure out, can he make it back to Gotham City in 1.9 hours? So Batman wants to make it back to Gotham in 1.9 hours. He's traveling, he's going max speed in the Batplane, but the wind is slowing him down. It's pulling him back a little bit. So we don't know how fast he's really going. We need to try to figure out, is this situation possible for him to get back in 1.9 hours? What we need to do are find these speeds. We need to know what was the max speed of the Batplane and what's the max speed he can travel with this slowed down wind. And we're going to see if that's even possible. Now keep in mind, I know the max speed of the Batplane. So we're going to find what speed has to work for the rate of this problem, and then I'll let you know if that's possible in Batman's Batplane. So first thing we need to do is really set up our unknowns here. Our unknowns are the rates. Now, we don't know how fast the max speed of the Batplane is, so we're going to let that be x. And when traveling back to Gotham City, we're still traveling at the max speed, but we're slowed down 207.6 miles per hour. So this is the speed that the plane is traveling as it's being slowed down. So we have our distance, we have our rates. We can say the first equation here, let me clear some space. This first equation, let's say distance of trip 1 going to Bataan. That is 1.8 times x. That's the rate and time multiplied together. Let's say the second equation, distance of trip 2 going back to Gotham City, is 1.9 hours times x minus 207.6. Okay, I kind of ran out of some space there, but we can go ahead and distribute this, and we're going to say, let me write it here, distance 2 is equal to 1.9x minus 1.9 times 207.6 is 394.44. So here is the equation for the distance to Gotham City, and here is the equation for the distance to Bataan. What do you notice about this problem and these two distances? How are they related to each other? Well, hopefully you're saying these distances are the same thing. Going from Gotham City to Bataan and going back from Bataan to Gotham City is going to be the same distance. We traveled the same amount. And how far was that distance? Well, keep in mind that that distance is 7,000 miles. Batman is traveling 7,000 miles twice, going from Gotham to Bataan and then back. So, how do we go about and set up this problem? What we need to do is basically set the distances equal to each other. So let me try and do this here. Distance 1 is going to equal distance 2, right? Distance of the first trip and the second trip, they're the same thing. So we're going to say 1.8x is equal to 1.9x minus 394.44. So we're saying both distance equations equal to each other. And let's solve for x. I'm going to minus 1.9x from both sides. So we should end up with, so 1.8 minus 1.9 is negative 0.1x. That's equal to negative 394.44. If I divide both sides by negative 0.1, I will end up with a positive 3,944.4. So this is the rate of speed the bat plane would have to go at max speed, okay? X here was, what speed does the bat plane have to travel at max? So what must it go if it needs to make it back to Gotham in time? Well, the bat plane has to, at minimum, its max speed would need to be 3,944.4 miles per hour. If the bat plane traveled that as max speed, Batman would make it back just in time to save Gotham. So that's how fast we need the bat plane to be able to go. 3,944.4 miles per hour. Now, is that possible? Well, if we look at the Batman canon over the years, we would realize that the bat plane actually can go 4,000 miles per hour. So we're in luck. Yes, Batman can easily make this speed. The bat plane can go 4,000 miles per hour, so we're fine. We meet the bare minimum that we needed to travel at to make it back in time. So Batman saves the day. I'm realizing now that this would be a very dark and grim problem if the answer was no, he doesn't make it back in time. Oof, that would be dark. But in this case, we understand, again, a way of representing the distances. Here, this problem is very much the same as the first problem we saw with Mr. Rosewig making the hike up and down the hill. The distances were equal. In the previous problems, we had the distances not being equal, but they added up to a total distance, okay? This is the general form that we need to work with. When you're working with distance, rate, time problems, you can really have two situations. Situation one, distances are equal. The distances are equal to each other. That means distance 1 is equal to distance 2. So if you found the rate and time for the first one, you can set it equal to the rate and time of the second problem, or of the second distance. So here we're seeing when the distances are equal, whether it was the Rosewig problem or the Batman problem, you set them equal and you set the rates and times equal to each other. The other situation was that distances are not equal to each other. If the distances were not equal to each other, what you typically have to say is that D1 is related to D2 with some total distance. So maybe you would say that D1 and D2 add together to give you some total distance. This is when you have two separate things traveling, right? Basically, two vehicles going towards each other or driving away from each other. Sometimes they'll say like two trains heading in the opposite directions from each other, whatever. Here we basically would have the distances not being the same thing, not being equal to each other, but they're related in that they add up to a total distance. Now, I will say there are other ways I can set this up. And I do set some of these problems up differently in the homework. So you'll see where the distances aren't equal, they don't necessarily add to a total distance. But you still need to find a way of saying how these two are in fact related to each other. You want to see how these distances somehow add up to a larger distance, or they make up some different components of a larger distance. Drawing pictures is crucial to helping you out here. It's a lot of information to keep track of. And when you draw a picture, it can be helpful to see this relationship between the distances, so you'll know whether or not they're equal to each other or if they add up to a total amount. If you have any questions on the problems we went over in this video, or would like to go over any more specifically, or if you have any comments, please feel free to let me know. My email is klinford, that's KLINFORD, @wccnet.edu. Let me know what you thought or if you have any questions, and until next time, take care.